So we can start. Once again, welcome everyone to this webinar. And today we will be talking about how to model Adobe shear walls using the ASDConcrete3D constitutive models. We already introduced this model in the previous webinar for modeling reinforced concrete shear walls. But of course, this model can be used also for masonry-like materials, so also Adobe. Now, we have our special guest, which is Professor Nicola Tarque from Peru. So the first 10 minutes, he will present his thesis, his work on Adobe, and then I will be modeling one of the many tests that he analyzed. So Nicola, you can go ahead. You can share your screen, you can do your presentation, and then I will go on. Thank you, Nicola.
Okay, Massimo, thank you very much. Good afternoon, everybody. I will just a moment. Okay, I think you can see my screen. First of all, I would like to send to the ASDEA colleagues for this kindly invitation. Always is a pleasure to collaborate with you and to show what we have been doing, what we have done in Peru regarding the experimental and numerical work about Adobe walls. I would like also to thank to all people from South America I'm seeing here from different countries and from all over the world. Okay, just 10 minutes. Please let me know, Massimo, if I go further than those 10 minutes, because when we are talking about these important topics, times go so fast. Yes. Okay, just a brief introduction why it is important to study the numerical behavior. Let's talk about Adobe walls now, but it can be translated into earthen structures, heritage, and also actual buildings. So the cultural heritage can be built also in earthen material, and we are trying to study the behavior of that material. So Peru is here located in South America, where just I will show the pointer. Okay, where the pointer is, and we are located in the Pacific Ring of Fire. As you can see here, there is almost a circle in red where the majority of earthquake occurs. Every year there are a lot of earthquake that in Peru we have in Peru. So our buildings should be constructed very, very well to support that dynamic actions. I forgot to tell you, some slides are in Spanish, but there is no problem because I will explain you what is the meaning of each of the figures. Just to be worried a little bit, this is a map of Peru. Here is the coast, where we have the subduction zone, and the red zone that you see, this is the seismic gap. The seismic gap means that in almost 300 years, we didn't have a huge earthquake. So the experts said that an earthquake of moment magnitude 9, we said 9, we will have an earthquake of moment 9 in Peru, close to Lima, in the coast area, and many damage we are expecting. So we need also to be worried about the behavior of our earthen buildings. What about this behavior? This is an unreinforced masonry building. Adobe, or earthen material, is a brittle material, with almost no tension strength. Easily, it can, when the earthquake comes, it attracts large inertial forces due to the mass and breaks suddenly. When it breaks, we expect collapse of them. Since you are familiar with the analysis of this type of building, you have seen that the typical failure or collapse mechanism in these unreinforced masonry structures are due to the disconnection of the perpendicular walls no, in these angles. You see that a huge vertical crack in this connection. This is what happened when every time an earthquake comes. So this is a typical behavior. Then we have, of course, the out of plane failure of these walls in many ways, combining also in plane and out of plane failure. Just to remind you that one block that dropped from this height, from the top of the building, may kill people. So it is important to prevent those damages. More figures about the out-of-plane behavior. In some cases, the roof may be okay or collapse, depends of the position of the beams, of the wooden beams. Normally, the walls collapse in out-of-plane behavior, and this is what happened in these structures, and this is why we are here, trying to understand the seismic capacity, the seismic vulnerability of earthen material. As I told you at the beginning, it is important to see that we are not only going to evaluate the walls, Adobe walls, we are also worried about our heritage. This was an important charge in the city of Pisco in Peru, when an earthquake of moment magnitude 9 came, destroyed practically all the church, losing the architectural heritage value of the entire city. This church was made in earth, and unfortunately, we didn't see what could have happened with the earthquake. We didn't put any reinforcement, nothing. So this is the results, no? The two figures show it here below. Another earthen structure, earthen church in Peru, typically the vault made with wood and mud, not stone or fire clay. It is usually made with wooden materials, cane and mud. Then the two towers, no? The two towers and the first floor made in Adobe. Again, the earthquake comes and almost the church was destroyed. Now there is another chart in another material, reinforced concrete, that guarantee that the behavior will be okay, but we have lost our our value, architectural and heritage value. So this is important just to show you why we are studying. According to ICOMOS, we have to follow a procedure to evaluate the seismic vulnerability. First of all, study the material, details, drawings, trying to understand how that building was built. Building means Adobe or church. Then to understand the seismic actions, and one of the most important points is to perform the numerical modeling, starting by a linear static analysis and ending with a non-linear dynamic analysis. And this is why we are here, to understand how to make these numerical models performing or modeling the material with non-linear properties. Then we need to, of course, to design the intervention, the strengthening system, and to reevaluate. But it is important. However, earthen materials, there is a lot of experimental tests made in steel, reinforced concrete, but in earthen material is too low. And we need to figure out what are the main mechanical properties, the values or the behavior of the constituent load in earthen material. And this is the work that I was doing 10 years ago, trying to make some parametric analysis to figure out the nonlinear behavior of these earthen materials. Sometimes in the laboratory we can calculate the compression, the tension, but what we call energy fracture energy is quite difficult to evaluate. So we did it with numerical modeling. The wall that Massimo will show you later is this Adobe wall tested in plane, cyclic in plane loading, tested by Professor Marcel Blondet and Julio Vargas from Catholic University. This was a project where I was also involved, trying to figure out what kind of low-cost strengthening system we can put in the Adobe walls. But today, Massimo will show you how to model this wall with nonlinear material properties. So we tested in 2005. This is the hysteretic curve, force times displacement, top displacement. And then 10 years ago, I did it with a commercial software, trying to evaluate and to reproduce what happened in that wall. No, see here I was imposing cyclic that displacement loading at the top, and then we were showing the X-crack behavior of that experimental tested wall. Of course, we had problems, we have some issues to solve, but this is what we did, the best that we did 10 years ago. The idea now, you can see, for example, here, the black line is the numerical one, and the gray line is the experimental one. As you can see, there is not almost a perfect match, but this is the most closer that we have at that time, trying to reproduce a cyclic behavior. And then we perform also non-linear dynamic analysis of an Adobe module. It could be maybe another topic with ASDEA colleagues, but today we are trying to reproduce the experimental behavior of this wall, but using SDKO OpenSys. I have more to show you, but I'm trying to respect the 10 minutes. This is my 2 emails I'm checking usually. In case you need further information, results, conclusion for papers, research papers that are already published in journals. So you can send me an email and I will show you, I will answer you later. Before, just to tell you that we also performed some dynamic tests, and maybe it could be a topic for a next seminar. No, this is a dynamic test that we performed in the Catholic University, and you can see here how is the out-of-plane collapse of this ASDEA structure, the in-plane collapse. This was made in a shaking table in Lima. I will reproduce it again. And we were able also to model with a commercial software that this dynamic behavior. The idea should be also to reproduce with SDKO OpenSys with a new material models and more sophisticated models that Massimo will show us. Again, thank you very much to all of you. And now I leave the room to Massimo.
Hey, thank you, Nicola. Very interesting as usual. Okay, so, well, Nicola did a lot of things in his research about Adobe. Now I will focus on just that experimental test that we showed at the beginning. So static analysis, but cyclic static analysis in the in-plane behavior. Okay, so let me share my screen. And I need to go on this computer. Here we are. Okay, so first of all, I will tell you what you will find tomorrow. Okay, by tomorrow you will have this folder. You will be able to download it from our website, and you will have 4 folders. Okay, reference articles, which actually I cannot share the articles. Okay, but I shared here a PowerPoint with all the citations and everything you need. And the most important things we need for modeling this from Professor Tarque's articles. Then we have the reference curve. This actually has nothing to do with Adobe, but there is a nice tool to simplify curves that comes from experimental test. I will show you this one in a while. And then I have the model that I will be doing today. For reasons of time, I will use a very coarse mesh, and I will show you that this model is very stable, and also with a very, very coarse mesh, you can obtain good results. And here I have a model that I already pre-run with a very fine mesh, just to show you the differences, okay? Depending on the mesh size. Okay, so let's start with the presentation. So here I will show you how to perform the same model that Nicola did previously, I think in Abacus it was, but now you can do it in OpenSys using the ASDConcrete3D. I already presented this material in the previous webinar, so I will not spend so many words on it. Instead, I will tell you how to calibrate it, because this material has some presets that are very good for concrete, but you will see that even though Adobe can be seen as a frictional material pretty much as concrete, it is not exactly the same. So you may need to calibrate some of the material parameters. So I will tell you how to start with a very basic template, which is where you just need one parameter, okay? And then I will tell you how to calibrate all the other parameters, like we will move to the 4 parameters and then the 6 parameters. Just a brief recall. So if you want to understand how this material works, you can access the documentation on GitHub, the OpenSys GitHub. So you can go here and you can see the documentation on how to use it plain from OpenSys, or in this webinar you will see how to use it from SDKO. And here you have a little bit of theory. Okay, so I will not go here, but here you have the basic equations from the elastic prediction to the unilateral effect. What is the shape of the failure surface? And by the way, in the OpenSys documentation, you can download files that I use to generate these surfaces. In the same way, you can understand how damage works, how rate dependency works, how the uniaxial material works. Okay, so there are files that allows you to calibrate this material test and to visualize it at runtime. Okay. And then there is some explanation about the implex integration scheme. So I will talk about it during the analysis. If you want more information about the implex integration, this one is the reference paper. Okay. And there is a new thing that I didn't explain last time, which is a feature that we have here in the ASDConcrete3D, which is the anisotropy of internal variable. I will talk about this one when we will do the test. Okay. Oh, by the way, before actually going into the model, yesterday we just released SDKO version 3.3.0. Okay, so you can download it because there are many nice new features. Okay. Okay, let's go on. So in the first 8 slides, you will find some theoretical background of the material. Then at slide 9, you will see the 2 references that I used. So in this reference here, you will see actually everything you need about the simulation of this Adobe wall. And if you need more information, there is the PhD thesis of Professor Tarque with more in-depth information. Okay. Now, if you cannot access the papers, here I just posted something that we need for modeling it. Okay. So in chapter 2, there are some details about the model. Okay. So it's an H-shape configuration where you have the main longitudinal wall, which is 3.06 meters long, 1.93 meters high, and 0.3 meters of thickness. And then this one is connected to 2 transverse walls, which are about 2.48 meters. Then on bottom and on top, you have a square section concrete beams. Here above the window opening, you have a wood lintel. Okay, so we will be modeling that because it can be very important. And what about the boundary condition? Here they are very simple. So you have a fixity here at the bottom. The top is completely free. So it actually can move as a cantilever. Okay. So if let me see if I can do a drawing here. Okay. So here, this one acts actually as a rigid plate. We will apply a load here at the center. Well, in reality, the load is applied here at the 2 sides, but it's not important because the concrete beam will be enough stiffer than the Adobe. So we will be applying a force here, and it will be displacement control. Now, the top is completely free, so it can rotate, it can uplift. Okay, so it's basically, it's free to uplift and to rotate. Okay. You will not see huge rotations because it is very thick. So basically the shear deformation will dominate. Okay. So clear all drawings. Okay. And at the end, this is what we will be trying to reproduce. Okay. So this is part of the, well, if you read the paper, you will see that you will find a larger force displacement, but actually they decided to stop the zone of interest at 10 millimeters more or less, because after this they experienced sliding. So the result was not stable. So we do the same here. So this is the kind of crack that we expect. X cracks here, and on the other side, of course, because this one is cyclic, and bending cracks on the two lateral walls. Then if you go on chapter 3.1 of Nicola's thesis, you have more information about the material test. Okay, as Nicola said, you can do tests here, you can do tests about compression and shear, but what is complicated is to get the fracture energy. In fact, if you look at the results that they have here, they basically have results up to the peak because it is not controlled, but they do not have any information about what happens after the peak. Okay, so here we will try to calibrate and try to give some values that you can use for the fracture energy. Okay, but from standard test, you will be able to have a compression strength, a peak strain, an elastic modulus you can have from these curves. And in the same way, you can have, thanks to diagonal compression test, you may have the shear strength of the wall assembly. Okay, so basically here what we have is a mean compressive strength of 0.8 more or less, and 9.6 to the -3 as peak deformation, and we have a shear strength of 0.026, a mean shear strength. Okay. Okay, so this is all we need. Let's go to ASDCO. Now, I will not show you the entire modeling, but it is very easy. So I will show you step by step what we have. So it's a single geometry. Okay, it's just a series of multiple faces. There is a cut here at the bottom. Okay, so this cut here at the bottom is used for creating the bottom surfaces, which are of concrete. Same thing here at the top. These ones are concrete, or if I go in property, it will be easier to see. Okay, so top and bottom is concrete. Then here in the middle, the dark brown is the lintel. So it's a wooden lintel. Here between the lintel and the Adobe, in the Adobe material, we have a thin layer of just a mortar. It's like a contact material. We just need it because the lintel will be elastic. But if we attach the lintel directly to the homogenized masonry, we will overestimate the tensile capacity of this one. Well, actually, the boundary of the lintel is the first thing that detaches from the Adobe. Actually, the only reason why we need a lintel in this kind of modeling is because we typically, let me do a drawing here. Because when you do a continuous model, like with shells or solids, you tend to assign distributed loads. Okay, so also here you will have distributed loads. Okay. Now the problem is that, well, not in this case, but imagine a multi-story building. The first thing that will crack during a lateral loading will be the plate, the zone here above. Why I cannot see the drawing? I cannot see the drawing here. Let me try again. Well, I was trying to draw, but for some reason I cannot. Let me do it here. Well, anyway, for some reason I cannot do the drawing here. The reason why you need a lintel is because this zone here is the first one that will crack in a multi-story building. And if you apply a load directly on this, and typically this is what you do, because when you have a continuous model, you apply distributed loads. When this one will fail, everything will try to collapse, okay? So you need something that avoids the instability here. So it is often necessary to model the lintel. Now, okay, here. Perfect. So, but the lintel should not be directly connected with Adobe. That's why, oh, here, now you can see the drawing. Well, this is strange. Okay, let me clear the drawings. Perfect. Okay, let's go ahead. And so here, between the lintel and the Adobe, we need a thin layer of contact. And I will show you how we'll do it. Then I have a cut here in the middle because I need a center point for the application of the load and for monitoring and to use it as a control node for monitoring. Then I have this condition here, which makes it a rigid body here at the top. And then I have another interaction here at the sides, which is not strictly necessary, but I will show you that it is necessary when you will use a very fine mesh, okay? Just remember that the shell has a representative thickness, in this case, 300 millimeters, but the geometry itself is just a two-dimensional surface, okay? So in this case, the mesh will be very coarse, okay? But imagine I use a very fine mesh, like a mesh like, let's say 15 millimeters, and then I do a drawing. You will see that now the center face is attached here only to something like to this zone here, which is 50 plus 50, and this one is only 100 millimeters, which is much less than the entire thickness of the wall, which is this one. Okay, so when you use a very fine mesh, it can be useful to do this trick here. So what I did was to simply add two other cuts here at the sides, okay, at a distance of 150 millimeters on one side, 150 millimeters on the other side. And then I created an interaction, which is called rigid links sides. If I edit it, you can see that I have a master, which is the center edge, like in this case. And then I have slaves, which are the faces here, okay? Oh, by the way, this is a new feature that we have in the new version of ASDConcrete3D. You can edit and you can visualize what is the master and what is the slave in a pre-created interaction, okay? So this interaction here is just used to make this one a rigid body, okay? So that it reflects the stiffening effect given by the thickness of the central wall. Okay, that's it. So it's not so complicated. This is a single geometry and you have only two interactions. One is to make the central node a control node, and the other is to make these two portions rigid with the thickness of the shell. Then what we have a linear time series. This one will be used to apply gravity loads. And then we are going to have a cyclic path time series that will be used to impose a displacement, okay? Now, by the way, let me go back and how do I generate this one? Well, if you go in the folder called reference curve, you will find an Excel file. Let me open it. Nicola gave me this data, but basically these one are the data coming from the laboratory test, right, Nicola? And for some reason it's trying to print something. But anyway, let me show you what it does. Okay, so here you have just two columns of the entire test. And I put, and let me remove this one and this one. Here you have all the displacement points, and you will see that it is a very dense curve. And here you have the force points. Okay, now I created a simple Python script that if you run it, okay, first it will print everything. Okay, so you can see that the entire wall has been pushed up to about 50 millimeters. Okay, but then if you read the paper, you will see that at about, I think, 11 millimeters, they start experiencing sliding So the results after 11 millimeters, 11 millimeters more or less were not reliable. So we need to cut it, okay? So if you look inside the Python file, you will see what it does, okay? But basically, okay, so first it will show the entire curve. Then it will tell, okay, the entire curve was 8,000 points. Now I'm cutting the curve to 11 millimeters, okay? So this one is the reduced cycle. And at this point, it is very dense because it is 6,700 points. After this, I'm going to perform a reduction, okay? So here you have a reduced curve, which is made only by 300 points. This is very useful because in this case, I'm going to use the displacement points as cycles. But if you have too many points, in OpenSys, you will do at least one step for each point here. And this one is going to be a little bit demanding, and it is not necessary to have such a dense curve, okay? That's why I decided to simplify it. Anyway, this is not extremely necessary, but it's nice. There is a tool that basically simplifies a curve, maintaining the quality of the curve, okay? So it can be useful for other purposes. So basically here you have F reduced and U reduced, and the content of U reduced is what I put here, okay? So 302 points of displacement, they are in millimeters. Then material properties, okay? So we have the elastic concrete section, this is the elastic modulus, Poisson ratio, thickness, 300. So concrete is going to be considered elastic. Then we have an elastic lintel section. Also here I use elastic membrane plate section, Young modulus, and so on. Now let's talk about the interface material. Now first I need to create a three-dimensional nonlinear material that simulates the contact behavior, okay? And then I will put it inside a plate fiber. A plate fiber basically is a cross-section of a shell, and you can simply choose a material, in this case the interface material, and the thickness, okay? And it will produce 5 integration points through the thickness using the same material. Now the interface material, also in this case, is an ASDConcrete3D. But in this case, what I want to create is a simple material that does something like this, okay? So in tension, it will have a strength, then it will go down, dissipating a certain fracture energy. It will always go to the beginning while unloading, so pure damage. And in compression, it will be purely elastic, okay? This one is only to create a contact with a damage in tension. Now, how you do this with the ASD? Well, you can define Young modulus as usual. Poisson ratio, that for contact 0 is fine because you don't need a real Poisson ratio. But instead of using one of the presets, you can go to user defined. When you go to user defined, you have the maximum freedom. So basically, both for tension and compression, you have 3 vectors. So here you have tensile hardening law, strain point. These are the total strain points. Then you have the stress points, and then you have the damage values. And same thing for compression. Now, just to explain you, for example, in tension, I put always 0 at the beginning. So imagine I want something like this. 0 at the beginning. Then I have this one, which is my tensile stress divided by E. So it will be this point here. And then an ultimate deformation at this point, okay? And the same thing here, but they are stress values. And then for damage, I use 1 and 1 because I want pure damage. I don't want plastic deformation in this interface. In compression, instead, only 2 points. So 0, 1. And here I put 0, 200 because deformation of 1 times Young modulus of 200 gives me this. This is just to simulate an elastic behavior, okay? Because after you have, oh, sorry, I stopped sharing. Okay, so when you have just 2 points like 0 and a point here, then what happens next will be linearly extrapolated. So if you just give 2 points and the first 2 points always coincide with initial stiffness, then everything will be linear extrapolated and the behavior will be linear. Okay, so clear on drawings. And if I do a test here, this is what happens in tension. because I'm not pushing it in compression. Let's push it also in compression. And this is what happens, okay? So in tension, you have a little bit of strength, then you have a damage, and then it goes back to zero, and it recloses in compression. In compression, it's purely elastic, okay? It's just to simulate the gap opening and closure. Okay, so this is very easy to set up. There is nothing special here. Once you have this three-dimensional material for contact, you put it inside a fiber cross-section. And now it comes the interesting part. So the Adobe material. Now I will show you how to calibrate it, okay? So let's skip it for a while. You have your Adobe material, you calibrate it, then you put it inside the plate fiber. So you choose the Adobe 3D material and you choose a thickness. In this case, it is 300 millimeters, okay? And then you just need a finite element, which is the ASD shell Q4. If you want, you can consider nonlinear kinematics, but in this case, it is not necessary. So I just kept linear kinematics. So just one material, just one finite element assigned to everything. And then boundary condition. As I told you, there is a simple fixity here at the bottom. Okay, so all the degrees of freedom are fixed. Let me move to conditions so it's easier to visualize. Then we have a rigid link here at the two sides, which is a three-dimensional rigid link of type B, which is basically a rigid body, okay? It remains flat, but it can rotate and move. But as I said, this is only important if you use a very fine mesh, otherwise it is not important. Then you have an equal DOF in the X direction here, because we apply the force only on the central point here, but we want it to be distributed on the entire wall, okay? So we just used an equal DOF. Here on drawing, this is very easy. Oh, by the way, equal DOF only in the X direction, okay? Because if we fix also the Y direction, the top wall will not be able to move, okay? So we need to allow a different displacement in the Y direction, okay? In such a way that it can move, but it should have the same displacement in the X direction, okay? So that's why I'm using only X. Okay, so very easy. And then we have self-weights, okay? So self-weight for concrete, it is applied only here, and it is going to be 24 kilonewton meter cube times the thickness. And this is the value that I need. Of course, you need to put a minus sign. Here we are working in Newton millimeters, so this one is the value, okay? And something else, same thing for the timber, the lintel, and for the Adobe, okay? So we just have 3 distributed vertical loads. There is no additional load in the experiment, so just the self-weight and the weight of the concrete beams. And then the imposed horizontal load. As I told you, it is simply a force here placed in the center of on the control node, basically. It is a force in the X direction. Now, we are going to do a displacement controlled analysis, so it is not actually important what this value is, but for numerical stabilities, it is important that this one is close to the expected value, or at least the same order of magnitude. Now here, I'm expecting something like 40 kilonewtons, but I'm working in Newton, so I apply here the value corresponding to 1 kilonewton, okay? In such a way that the load multiplier will correspond to the total load in kilonewtons, which is what I need to compare with experimental tests, okay? So 1 kilonewton here of imposed, this one here is 1 kilonewton of imposed value at this point, okay? Cancel, and then let's see the results, the analysis steps. So the first one is always the recorder. We're going to use displacement, reaction force, and then we want to see section force and deformation for the shells. Then if we want to look into the fibers, we can look at fiber stress, strain, damage, and then we have some interesting new values here, and they are pretty nice to visualize, and I will talk about them now. It is supported only by the ASDConcrete3D, and it is called crack pattern to visualize the opening and the inclination of the cracks in tension, or crash pattern for compression. Now, in this example, you will not have any compressive failure. It is only going to be shear failure dominated by the tensile part. So you will see results only here. Very few things here, I think. Okay. I will talk about these results later on. Now, to save time, I decided to record every 10 steps, just to have an output which is not too heavy. Then, after the recorder, we place the constraints. Very simple. We have just one single point constraint, the fix it at the bottom. And we have two multi-point constraints, the equal DOF on top and the rigid link on the two sides. Then we have gravity loads. So it is a load pattern with the linear time series and the three distributed loads that simulate the entire self-weight of the system. Then we perform a gravity analysis. Okay, so it is a static analysis. We decide to use the penalty method as a constraint handler, and then everything is set up for parallel analysis just to speed things up. Okay, but I've been talking about these over and over again. So the only important thing is that it is load control, total duration of 1. I'm not going to expect any nonlinearity in the gravity analysis, so I put just one step. And if something goes wrong, anyway, I have adaptive time series. After this, always remember to keep the load constant and reset the time step to 0 before you do a displacement controlled analysis. This is very important. So gravity loads will be kept to 0. It will be kept constant at the current value, and then you can safely reset the pseudo time step to 0 for the next analysis. Now, before running the next analysis, we need to apply the horizontal loads. Now, the horizontal load is a nodal load, so it goes here, which is the imposed load. And the time series should be a ramp, should be a linear time series, because actually the magnitude of the load is decided by the displacement controlled analysis. Okay, so this is very important. Otherwise, you can do something different. You can do a load control analysis. You can apply an imposed displacement, and in this case, you can use the cycle as the time series. Okay, but in this case, I will use a ramp. I will use an imposed load, and I will do displacement control in the analysis step, in the final analysis. Okay, so once you have the load, before running the analysis, I define a monitor. Okay, so I want to create a monitor plot. The plot is going to be called Cyclic test Adobe. Now, for the x-axis, I want to plot the displacement along the x component at the selection set number 2, which is control node. Okay. Then I took average. It's not important because it is only one node. But remember that in parallel analysis, this one can be important. Why? Because if I partition this mesh here, exactly at the middle, okay, this node, the same node, will be on two partitions. Okay, so if I sum the displacement of the two nodes, I will see double the displacement. Okay, so just to make sure, every time you do a monitor in parallel analysis of a single node, okay, just put average. Okay, so if it is on a single processor, it will be fine. Just the average of a single value is the single value. If that node is on multiple processors, it will do the average, but in any way, in each processor, that node will have the same value. Okay, so for example, you have displacement of 2 plus displacement of 2 divided by 2. Okay, so the value is the same. Now, in the y-axis, I can choose to record either the reaction at the base, which is recording multiple nodes, but in this case, I'm doing a displacement controlled analysis. And if you remember, I applied here at this node a reference load, so ref is equal to 1 kilonewton, right? So the total analysis will be the total load, so the total imposed force will be the lambda, which is the pseudo time step, times the reference load, right? But if the reference load is 1 kilonewton, then lambda is the total result in kilonewton, okay? So that's why I decided to record the pseudo time as the reaction force, okay? Because it is actually that. Okay, and then I have a background plot, which is the plot that I told you before, okay, the simplified plot. Then I want to append millimeters on the x-axis because the results are given in millimeters, and kilonewton in the y-axis, because the load multiplier will be in kilonewton in this case. So cancel, and now the analysis. Cyclic analysis, once again, static penalty. So the settings are the same as the gravity analysis. The only difference is that the integrator this time is going to be a displacement control. And since I'm going to do a parallel analysis, it will be a parallel displacement control. The control node, the selection set for the control node will be selection set number 2. The degree of freedom, number 1, because I'm going to control the x displacement. And now I can either do a monotonic analysis by specifying the target displacement or a cyclic pushover using putting this one, so checking the cyclic option. And then in this case, instead of putting a value, I can select a time series. And that's why I created the cycle time series here. Okay, so it is very important that this time series contains the absolute values of displacement. And then adaptive time step, as usual, because if you have no linearities, you may want to allow OpenSys to resize the time step if it finds convergence issues. And then the number of increments. How do I decide the number of increments? Well, let's see. Let's open the cycle a little bit, and I will tell you what ASDCO does, okay? Because when you do a cyclic displacement control analysis, it's difficult to understand how many time steps I want, okay? So in cyclic displacement control, what I do is to take this time series, then I monitor what is the absolute max, which is in this case is this point, for example. What is the absolute minimum, which is this point? The delta is going to be max minus mean, so it will be 20 millimeters. And I decided to divide it in 300 steps, okay? So for me, it's fine to have 20 millimeters, sorry, not meters, divided by 300 steps. So this one will be my displacement increment, okay? So at least you have an idea of how large this number can be based on the type of increment that you want, okay? Clear on drawings, and clear this one. So the analysis actually will be longer than 200 steps. 200 is just because I have 20 millimeters and I want to proceed at a step of 0.2 millimeters. Okay, so that's why I divide, sorry, 0.1 millimeters. That's why I use 200. And after this, you don't need to do anything else because this is the end of the analysis, okay? Now, this is the entire setup. Now we are going to calibrate the material parameter. Now, this one is the one already calibrated, but now I will start from the beginning, okay? So I will tell you how I calibrated this for Adobe, because as I told you, this is a material that has been developed for concrete, but it can be used also for other concrete-like materials like masonry or Adobe. But probably you may need to calibrate something. Okay, so let's start from the very beginning. Imagine you are using this material for the first time. So you go here and here, and this is the default that you have. Okay, now we don't need a mass. Okay, the elasticity, well, you always have this one. From the experimental test, we had a Young modulus of 100 megapascal and a Poisson ratio of 0.2. Okay, so the elasticity is the only thing you are almost sure about. Then we have, here is where we have to play with the parameters, okay? We have the integration scheme. I already talked a lot about implicit and explicit. Now we will be using explicit because it will be much faster, okay? And then these two things down here, you can leave them as they are. I will talk about the crack planes in a while. I will show you what it is. But the first thing that you do when you do this calibration is, okay, let's move to Implex so the calibration will be faster. Then let's start with the easy preset. So the easy preset is the concrete one parameter. So with just one parameter, which is the compressive strength, everything is set up automatically by SDKO, okay? So let's try to do this. The compressive strength was 0.8 more or less, okay? So we don't need to be extremely precise. So just put 0.8. Now what happens here is that using the one parameter, I will be doing something like this. So it will be, well, let me try to annotate here. Let me see if I can visualize it. Okay, so when I choose the one parameter, so I only specify FC, SDKO computes FT as FC divided by 10, and then it decides that epsilon C is equal to FC divided by E times 2, which is the typical equation that we use for concrete, and then the two fracture energies. GT will be equal to 0.073 times FC to the power of 0.18. Okay, so this one is the equation for the tensile fracture energy of concrete given by the FIB model code, and GC is equal to 250 times GT. Okay, so this one is this one are the parameter already calibrated by SDKO when you choose the concrete 1P. Now let's see if it works, but probably the main error will be FT, because FT will be set equal to 0.08. So this one will be 0.08, which is much higher than the tensile and shear strength that they computed here, which is 0.026. So I'm expecting to overestimate almost by a factor of 2 the total capacity of the wall. Okay, but let's start with this. So we try to understand what are the parameters that are important. Okay, so clear all drawings. And let's start by this. Okay, so the only thing we are sure about are the elasticity and the compressive strength. Okay, now the mesh is a quadrilateral mesh, but of course I'm going to use a much finer mesh now. So 600 millimeters. So you see a very coarse mesh, but I will show you that at the end we will obtain a very good result also with this very coarse mesh. Okay, so let's run the analysis parallel, because I decided to, of course, I want to use 4 processors. Okay, so I partition it in 4 pieces. Done, and then I save it and I run the analysis. Will be very fast. Let's just wait. Oh, now one of the other features is that now the monitor has a tip point here, so that you can understand where it is along the analysis. Okay, and of course I'm expecting an overestimation here, and it is about twice, because it should be about 40 and I am at about 80 here, well 71. Okay, it is fine. It is fine because I was expecting that. Now, one thing that you can see here before starting to calibrate this one is that first I'm overestimating it, but I was expecting it, because now my FT and so also the shear strength, because of the shape of the concrete, is going to be almost twice the real, or even more, twice than the real strength that they computed. So it is 0.08 against 0.026. So it is fine, this overestimation, but something that I don't like is that it soon drops. Okay, you see here, I have a damage here. Here I'm reaching 80, then I go down to 60. When I'm here, I'm failing again at about 60, and I go to 40. And then when I'm here, I'm again at 40. Now this makes sense in an homogeneous material, but not so much in this kind of material, because basically what happens here is that when I'm loading here, I'm creating a crack. But when I go to the other side, there should be almost no damage. Something, because of course, the first crack influences a little bit the second one. But in this direction, I'm still virgin. So I still have to develop a crack. okay? So that's why I don't like that when I have a crack here, I go to the next side and I still have the same reduced strength. I want to be going something like here, okay? So how do I solve this problem? And this is the reason why we introduced the crack planes, okay? So you can go here, you can understand how it works, but basically, we want to have the internal variables stored at multiple crack planes. So if you choose this one, you activate the anisotropy of internal variable on multiple crack planes. Now, if you go to the documentation, you will see that you can decide how many crack planes you want for every 90 degrees. So imagine a material point is a sphere. Well, I'm doing only 2D. When you have a crack, for example, in this direction, okay, it affects the stresses in this and this direction. So actually, I need only one hemisphere. So the number of cracks here is the number of subdivision I want a 90-degree circle. Okay, so let's clear. And you can always leave it at 4. 4 is a nice parameter here. You don't need so many crack planes. 4 means that every 20-25 degrees I have a crack plane. Now this one is a smoothing angle. What is a smoothing angle? Is this one. If you see here, for example, if I am at a crack of 0, I will develop a damage, for example, a damage of 1. But then I want the near cracks here to be influenced by that damage, because it is not there realistic that if I am a damage in a direction, and then I move on about a couple of degrees, I don't have any damage, okay? So this one actually activates the smoothing. So if I have a damage here, I will have a damage in the neighboring cracks, but not in the cracks that are completely on the opposite sides, okay? So here, what I do typically for concrete is to use 45, but masonry-like materials, so material made of bricks and mortar, they are more anisotropic, so I tend to use a smaller value like 10 degrees, okay? Now, let's try to run this and let's see the difference with the previous. So if you remember, we had something like this. Let me rerun the monitor for a second. So the strength is here, but then we soon drop at this point. You see a rapid accumulation of cyclic damage. Okay, so let's run the analysis again, and let's see what happens. So we still have an estimation now, another estimation of the capacity, because we still need to calibrate FT, but I want to see a better cycle now. Okay, now you can see that now the damage is not accumulating as fast as before, okay? But we still have this huge overestimation, okay? So let's stop the analysis now. So this is the first thing that we need. I typically always use crack planes. I start with the default, which is 45 for concrete, and I use a smaller value like 10 for masonry or other anisotropic materials, okay? And now let's start calibrating the parameter. So FC is fine, but I don't like how the one parameter computes the other values. So let's move to 4 parameter. Now in 4 parameter, okay, I can change some of them. For example, here, instead of using 0.08, which was the default computed by the one parameter, I can input the real one, which was 0.026. 0.026. And what about the fracture energy? Well, let's start with the ones computed for the concrete, because for sure Adobe will be more brittle than concrete. So we will try to lower it. But at least if we start with the ones given for concrete, we have an upper bound, okay? And then we start to calibrate. You know, when you calibrate material, especially when you calibrate values such as fracture energy, it is very difficult because you don't have so much information. It's difficult for concrete. I imagine for Adobe is much more complicated. So it is very important that you have at least an upper bound. Okay, so let's press OK for a while, and let's do what the concrete would do. Okay, so here, let me zoom it. FC is going to be 0.8. Now for concrete, we typically use an equation like GT is equal to 0.073 times FC to the power of 0.18. And in this equation, it is very important that FC is given in megapascal. So this one is going to be the tensile fracture energy, and GC is equal to 250 times GT. Okay, so this one is what we have for concrete. And let's print it. So GT and GC. So we start with them, but at least we know that they are an upper bound. So we may want to lower them. Okay, so let's start with them. We have 0.07 in tension and 17 in compression. So we go here, 0.07 in tension and 17 in compression. Okay, let's see what happens now. Press OK, save, and run the analysis again. Now, since this one is the fracture energy of concrete, I'm still expecting an overestimation somehow, and I will explain you why. But it is fine. It should be like this. Okay. So you see here a slight overestimation, even though the tensile strength was fine, and I will explain you why. Okay, we can safely stop it here. We don't need to run it anymore because we can already see what is the problem. Okay, so let's zoom a little bit here. Except from the cycle we will fix it. But if I zoom here, it seems that I'm overestimating this one. Now, something that you may find interesting in tensile fracture energy is that, okay, but if I'm overestimating this capacity here, so probably I have to keep on lowering the tensile strength. And this is not necessarily true because, for example, my tensile behavior will be something like this. Okay, so if this is my FT and I change GT, I'm only changing how fast this energy will be dissipated, but I will not change the strength. So you may say, okay, but if I change GT, I will only change how fast this curve will go down, but I will not change the capacity here. Well, this is not true. This is true in a pure uniaxial test. But once you're doing a multi-axial test, like in this case, which is a complete building, in this case, it's a wall, it is under shear. What happens is that when your model, in this case, it is a wall like this, starts cracking here due to the first softening, before the entire system, and imagine the first cracks happens here, the first time the system goes down in softening is when the crack is completely open. But if you overestimate the tensile fracture energy, the crack will develop in a much slower fashion, and so it will allow the system to have an overestimated strain hardening, apparent strain hardening. Okay, so that's why GT can influence the strain hardening first and then the softening. Okay, now let's validate this thing. So we know that these values are an upper bound, so we may need to lower it. Now, how much? We don't know because they didn't have experimental tests. Okay, so we need to calibrate them. Okay, let's start by taking more or less 1/2 of 0.6, this one. Okay, so I will try 0.04 and 8. So a little bit more than 1/2 of the ductility of concrete in this case. it is pretty reasonable. So at least I know that I cannot be more ductile than concrete. Okay, so let's try this one. Save and run. Well, of course, I already calibrated. So I first tried 1/2, and then I came to 0.04. Okay, you see here now it seems pretty fine. Okay, now there is another problem. Now that we calibrated the first tracking here, we can see that the cycle is a little bit too much. We are dissipating more energy than what happens in reality. Now, this one is due to an overestimation of the accumulated plastic deformation. So a material as concrete is made of something like plasticity and damage. So in pure plasticity, you go down, you unload parallel to the initial stiffness. Okay, so this one is E and this one is E. In pure damage, you unload to the center, so no plastic deformation. While in concrete, it happens something in between. So the unloading modulus is something like 1 minus D, which is a damage variable, the initial elastic modulus. Okay, so we may need to calibrate how much damage my model is developing. Okay, now I'm still using, as you can see here, oh, let me open it again. So the curve is pretty fine now, but what I still need to calibrate is the amount of plasticity and damage to have a not so fat hysteretic curve. Okay, so how can I do this? Well, in the 4th parameter, I cannot calibrate the amount of plastic deformation. Okay, I only have FT, FC, GT, and GC. But I have another parameter here. I have another preset, which is called 6 parameter. Okay, with the 6 parameter, I have the 4 parameters as before, but I can scale the initial amount of plastic deformation that is calibrated for concrete, and I can scale it. So if I use 1, I will use the same amount of plasticity that I calibrated for concrete. But in this case, it appears that for masonry, and in this particular case, Adobe, the plastic deformation, at least in tension, should be lower. How do I calibrate it? Well, let's try to do the same. Here you can go from 1 to 0. 0 means 0 plastic deformation, but we already know that 0 in this case is not fine because we do have some plastic deformation. So let's try by divide it at 1/2. Okay, so 1/2 of the plastic deformation that I would choose for concrete, and rerun it. Oh, let's start by 0 first. I want to show you that 0 is not fine, but in this case it was obvious. But let's start by 0. And let's see what happens if I do not allow any plastic deformation in tension. So basically in tension, it will do something like this. It will unload the center, while in compression, it will have a certain plastic deformation. Okay, but in this specific case, since this wall is not a lot pre-compressed, I'm not activating the compressive nonlinearity, at least not at the very beginning. So you will see no plastic deformation behavior. Okay, so let's start by, okay, we use 1 is too much. Let's go to the opposite side. So we do a divide and conquer approach. Let's see what happens with a 0 plastic deformation in tension. Okay, I can already stop it here because you can already see what's going on. You see, when I develop damage in shear due to the tensile part of the model, what I have is this. Okay, so I damage, I unload to the center. Now it's not exactly the center here because I have a certain level of pre-compression. Okay, so this gap here is given by the pre-compression that I gave to my model. Okay. And then I go to the other side, I develop the other damage on the other side, and then I load to 0. But what I need is actually a certain plastic deformation in the middle. Okay, so 1 was too much because it was doing something like this. 0 is too low, so I need something in between, something that allows me to do something like this. Okay, which is basically what happens also in reality. So you have this first part here, and then a plastic deformation, and same thing here. Okay, so let's start to calibrate it. When I do this kind of calibration blindly, I typically do a divide and conquer. So the 1 is too much, 0 is too low. Let's put it in the middle, like 0.5. Let's see what happens. We are almost done. Eh? You see, now it seems much better. Okay, so this one is fine. Now you can still keep on trying to calibrate it, but for me, this one is more than enough. We calibrated very quickly the capacity here, the amount of brittleness in terms of fracture energy, and now we are calibrating the amount of dissipated energy in the loading cycles by playing with the amount of plastic deformation that we allow. Okay. And this one is fine for me. Okay, so we are almost done, 80% of the analysis. And you can see the effectiveness of this model. You can see that in about 1 minute, we are done with the analysis. The analysis is pretty stable. And then I want you to see that even if you are using a very coarse mesh, this one is giving almost the same result of a model that I already run with a very fine mesh. Okay, so we have 1 minute of analysis. This is the output that I have. And I already run the same analysis here with a very fine mesh. This is the output that I obtained for the very fine mesh. Now, if you want to compare the two, you can simply do something like this. I can copy the ASDConcrete monitor and the launcher outside here. So if I launch the monitor now, it will parse all the folders for the different curves that it finds. And in this case, it will find two plots. So if I plot all of them, you can see that they are really close to each other. So the finer mesh is not actually changing that much. It will be only much better for visualization. And this is what I want to talk to you about. So regarding the calibration, this is what you need to understand. When you try to calibrate material parameters for something like Masonry or Adobe, well, typically you always have information about elasticity. Something that you have for sure is the FC. And you have FT if you have shear test, like in that case, okay? The problem is that you don't have any information about the tensile fracture energies and the amount of ductility that you have because you don't have cyclic test. So one thing that I typically do is that, okay, it is a frictional material pretty much like concrete, okay? It is less precise than concrete. So I will try to first use the equation that I have available for concrete, and I will use them as an upper bound, okay? And then I try to lower them, trying to calibrate these parameters. In fact, as you have seen, I had to reduce by almost a factor of 0.5 both the fracture energy, but also the amount of plasticity. So in general, I'm making it twice as brittle as concrete. This is the idea. Okay, so this is all about the calibration. I just want to briefly show you in 5 minutes the output. So what you can get in terms of overall behavior, it is very fine, even with a coarse mesh. I will show you the output. The only bad thing about a coarse mesh is the output for creating a plot, okay? So if I look at the output here, you can see that, well, if I look at the displacement, it's fine. I can see that the discontinuity here. You can do an animation to see what's going on. If I try to visualize the cracks, okay, I can use surface color map, and I can go in section deformation, and I can visualize, for example, the maximum principal deformation. Okay. By the way, you can see that I have huge values here at the contact between the lintel, of course, because it's the one that is opening the most. but I can hide it by selecting the interface section and hiding it, okay? And now I can typically use either a hot preset here, or I created another preset called crack, which is something like I put a red here, a white here, and then another red here in the middle, so that I can give almost a constant value for the crack, okay? So if you do an animation here, you will see that you have diagonal cracks, but they are not pretty clear, okay? Because the mesh is very coarse, okay? Now, if you compare this one, if you run this one with a very detailed mesh instead, which is this one, and the analysis of the fine mesh took about 1 hour, okay, against 1 minute. So in terms of overall behavior, it's the same, but for graphic purposes, it will be much better, of course, because if I open the results with the very fine mesh, well, first of all, also in terms of displacement, you see a much better localization. Let me increase the deformation to 10. And then I want to show you the same thing, section deformation, principal maximum deformation. I put a 0 as a minimum, and then I use the crack one. I switch off mesh edges. And you can see now as the crack develop. Okay, so in this case, the visualization will be much, much better. Okay. So it's just that in terms of how you can visualize the cracks. If you use a fine mesh, you can see actually the direction of the cracks. And that's why we decided to use another tool, okay, which makes the crack plot very nice also for a very coarse mesh. Because in terms of result, it's fine. In terms of speed, it's much better, the coarse mesh. For post-processing, the coarse mesh is not so beautiful. That's why we came up with a new plot. Okay, so this one is very nice. We already know that, but now we want to have nice plots with a coarse mesh. So with a coarse mesh, instead of using the color map and the maximum deformation, now we created a new plot, which is called crack plot. And the crack plot works with this result here, crack pattern and crash pattern, okay? So if I go here and I create a crack plot, this is what you will see, okay? Now, let me just explain you what it is. First of all, is a result on each fiber, okay? So for each element, let me just isolate one element, for example, this one. For each element, you have 4 integration points, and in each integration point, you have 5 points to the thickness. That's why you have 1, 2, 3, 4, 5 symbols on each point, okay? But now in this case, it is in plane, so if you look at the sides, you will not see many of them. Now, what does it represent? Well, it is a circle, it is a cylinder that represents the opening of a crack, okay? So imagine I have a crack like this. So imagine I have a crack which is here. The normal to the crack is this one. Okay, so I draw a cylinder around the crack. Okay, the direction of the cylinder is the normal to the crack. This one is the plane of the crack, and the thickness of the cylinder is the crack width. Okay, so you have an information basically of the orientation of the crack and the opening of the crack. And for each integration point, you have at most 3 cracks. Well, in the model, you have more of them. Okay, because you have, in this case, you have 8 cracks, 8 crack plane per point, but I only show you the 3 most open cracks, because actually what you need are almost there. Okay, you don't need more than 3 cracks for visualization. Okay, so once you have this, you can have a cleaner output. You can hide the side walls because we don't need them. Yes, this one. Then you can go on the front and you can clearly see the cracks where they are developing. And for this, you can create a new color map, which is all black. Basically, you can create a new color map like this. You give it a name and you put 0 and 0 on the 2 sides. Okay, so in this case, you have a nice plot of the crack opening and orientation, and you can do some nice drawing with this. Okay, so let's run an animation with this, and it will be much clearer with respect to the in-plane deformation. Okay, so here you can see the evolution of the cracks and their orientation in space and their opening. Okay, so this is a new tool we developed for visualizing the cracks in shear walls. Okay, so I think that is all for this webinar. I think we have 5 minutes for questions, and something else before we finish. Nicola asked me to repeat this webinar, but in Spanish. So I think we will do it probably next month. Okay, but I will talk with you, Nicole, and then we will decide when we want to repeat the same webinar, but in Spanish. Okay, so thank you, everyone, and now we have some time for questions.
Just Massimo, to let you know that I was receiving some chats, private chat, that yeah, I was telling them that in the future, maybe in 1 month or less, we will repeat this in Spanish, because there are people working on modeling earthen walls in Ecuador, Peru, and in Colombia also. Professor Daniel Ruiz is also here in this seminar, and they are also working, doing a good job in tapial constructions, experimental tests in tapial constructions in Colombia. There is a question.
Yeah, there is a question. Sebastian, please go ahead.
Hello, thank you for your nice presentation. But I saw that there is a 9-parameter case, no?
Yeah, sure. I forgot to tell about this. Yeah, there is the 9-parameter case allows you to further calibrate the compressive part. Good question. Let me just briefly explain it, because in this case it was not necessary, because compression was not governing anything. But it's right, I forgot to explain it. If, for example, in this case, I have for compression only FC and GC. Okay, so epsilon P will still be, so the peak strain, which is this one basically. So this one is FC, and this one at the base is epsilon C, and this one is GC. Okay, so the compressive fracture energy. Now here you have a residual plateau, which is FCR, which is equal to FC divided by 10, and the peak strain, so this abscissa here, is equal to epsilon C equal to FC divided by E times 2. This is the typical equation we use for concrete, okay? And it's pretty good also in this case, because if we do a quick calculation, we have 0.8 divided by 200 times 2, okay? While instead it was 0.09 from the experimental test, if I recall correctly. It was 0.009, okay? So it was almost the same value, so I did not decide to calibrate it. But if you want to calibrate the peak strain or the residual strain, you can go to, or also the FC0, which is this point here. So up to here, to FC0, you are elastic, and FC0 will be equal to FC divided by 2. Then from this point to this point, you go nonlinear, then you go down linearly, and then you have a residual plateau. Now, if you want to calibrate FC0, like you want to start nonlinear before, or you want a different residual plateau or a different peak deformation, you can go to the 9-parameter, and you have this one, okay? So FCP will be this one. You can change FC0, you can make it lower, and you can change FCR and epsilon CP, which is this one here, okay? So the 9-parameter is to further allow you to calibrate the compressive part, which in this case was not playing a role. That's why I didn't calibrate it, okay? But if you need, you can do it.
Okay, thank you very much.
There are other questions? Nicola, how do you think it was compared to Abacus, the calibration? You think it's fine? You think there is something else that can be
It would take his thesis like a month instead of 3 years, probably. And Nicola, how long did he run like in Abacus? Like 8
Yeah,
hours?
normally in commercial software, it takes more time. No, it takes more time.
Say
This
the
work,
time, don't be shy. How long did it take the cyclic analysis?
it takes more time, more hours
Yeah.
for running the model. The advantage of SDKO is just in 1 minute you can have good results. Of course, this we were showing, or Massimo was showing, the calibration of the material parameters, but since you are familiar with them, you can perform the analysis very fast, and not only for one wall, as I told you in the minutes before, an entire building for the seismic vulnerability analysis. This is why it is important, of course, that this conference seminar, Massimo was showing just the calibration of one wall, but since you will get familiar, I mean, talking with all people who are here now, it could be used for entire building. And that's it. So it is a good advantage using SDKO because the time running, the time cost, time computational is very, very low. 1 minute compared with 3 or 4 hours it is good.
Yeah, also because this material seems to be pretty stable with a very coarse mesh. So you don't need to use a very fine mesh. As I told you, when you write a paper, yeah, it's better to have a very fine mesh because it's nice. You obtain nicer pictures of a more detailed crack. But in this case, you can see that the results are basically the same. With the crack plot, you still can obtain beautiful pictures. But in 1 minute, you have the cyclic analysis super fast.
Yes.
And yeah, so we can do the next webinar. Well, we can repeat this one even in 2 or 3 weeks from now. Then we will talk about it and you will tell me when it will be better for you in Spanish. So it will be easier for Spanish talking people. And yeah, I don't know if there are other questions. Otherwise, we can stop here. And thank you.
Yes, just to let you know that also Professor Xavier Cárdenas from Ecuador and his team is here, and they are also modeling some facades, earthen walls in Ecuador. So I hope we can collaborate in the future for doing more analysis with this. And any question, just feel free to contact Massimo, Guido Camata, and myself for interacting. And that's it. And
Gracias, Nicola.
From my side, just to thank you again to all my ASDEA friends, colleagues, and friends, and say hello again to all the people in this talk, and be happy. I'm happy to be here with you. Now, time for other talks.
Yeah, maybe in 3 weeks you can come to our place, so you can, when it's in Spanish, you can give the talk from our office.
And also we can co-organize it with the other universities in South America. So
yeah.
That's it.
Okay, and don't forget, by tomorrow you will have the files online. Okay, so you can download the files and you will be able to see the recording of the video. And of course, don't forget to download the latest version of SDKO because these new features are in the latest version. Okay, so thank you everyone, and thank you Nicola, and see you in the next webinar.
Muchas gracias.
Ciao Nicola.
Ciao Guido. Ciao Massimo. See you. Bye.
Bye everyone.
Bye Larissa.